Equipment Lesson 2 covers X-ray production and the X-ray beam. We're going from how electrons are produced at the cathode to how they interact with the anode to produce two distinct types of radiation, how those types combine into the emission spectrum, and how changes to kVp and MAS shift that spectrum. This is the physics of what you're working with every time you press the exposure button. 15 minutes. X-ray production begins with thermionic emission. The tungsten filament is heated by a low-voltage current, 3 to 5 amps. As temperature rises, electrons gain enough thermal energy to escape the metal surface. This creates the space charge, a cloud of free electrons surrounding the hot filament. The MA station on the console controls filament temperature. More heat means more electrons boil off means higher tube current. Emission increases exponentially with filament temperature. A small temperature change produces a large change in tube current. At low kVp settings, the space charge effect limits how much tube current you can achieve. The space charge cloud partially repels incoming electrons, creating a ceiling on MA at lower voltages. Once electrons are freed, the high voltage applied between cathode and anode accelerates them across the tube at tremendous speed. At 100 kVp, electrons reach approximately half the speed of light. Their kinetic energy at impact equals the charge on the electron times the voltage applied, in electron volts. That maximum kinetic energy determines the maximum photon energy the beam can contain. This chart shows the X-ray emission spectrum at 80 kVp. The x-axis is photon energy in kiloelectron volts. The y-axis is the relative number of photons at each energy level. The orange continuous curve is Bremsstrahlung radiation, approximately 80 to 90% of the diagnostic beam. The curve rises from 0, peaks around 1/3 of the maximum kVp, and drops back to 0 at the maximum energy, which equals the kVp setting. At 80 kVp, no photon can exceed 80 kiloelectron volts. The purple spikes are characteristic radiation, discrete energy peaks at approximately 57 to 69 kiloelectron volts, which are the characteristic energies of tungsten's K-shell electron transitions. The left edge of the curve is lifted off 0 by filtration. Inherent and added filtration remove the lowest energy photons, those that would only add skin dose without contributing to the image. 3 numbers to memorize from this chart: maximum energy equals kVp, mean energy approximates 1/3 of kVp. And the beam is 80 to 90% Bremsstrahlung. This slide shows two spectra side by side, 60 kVp on the left, 100 kVp on the right. Increasing kVp does 3 things to the spectrum. The entire curve shifts to the right, higher mean photon energy, harder beam. The maximum energy point on the x-axis moves to the right, from 60 to 100 kiloelectron volts. And the area under the curve increases, more photons of all energies are produced. This means increasing kVp simultaneously improves beam quality and increases beam quantity. The clinical implication: higher kVp produces a more penetrating beam that requires less MAS for equivalent density, which reduces patient dose. The 15% rule formalizes this: increase kVp by 15% and you can cut MAS in half while maintaining equivalent image density. The result is approximately 50% dose reduction. This is the primary optimization tool in digital radiography. Bremsstrahlung is German for breaking radiation, and the name describes the mechanism perfectly. An incoming electron passes close to the nucleus of A tungsten atom. The strong electrostatic attraction of the positive nucleus decelerates the electron. The kinetic energy lost in that deceleration is emitted as an X-ray photon. The energy of the photon depends entirely on how close the electron passes to the nucleus. A near miss produces a high-energy photon. A distant interaction produces a low-energy photon. Because this distance varies randomly across thousands of interactions per second, the result is a continuous spectrum of photon energies, from near zero up to the maximum kVp. Bremsstrahlung makes up 80 to 90% of the diagnostic X-ray beam above 70 kVp. The useful imaging beam, the continuous curve on the emission spectrum, is almost entirely Bremsstrahlung. kVp adjustment shifts the entire Bremsstrahlung spectrum. This changes both beam quality. Characteristic radiation follows a completely different mechanism, and it only occurs above a specific kVp threshold. Step 1. An incoming electron carries enough energy to eject an inner shell electron from a tungsten atom entirely. For the K-shell of tungsten, this requires the incoming electron to have energy greater than approximately 69.5 keV, which means characteristic radiation from the K-shell only occurs when the tube kVp exceeds approximately 70 kVp. Step 2. An outer shell electron drops down to fill the K-shell vacancy. This transition releases energy, the difference between the two shell binding energies. Step 3. That energy difference is emitted as an X-ray photon with a specific, discrete energy. For tungsten's K-shell transitions, those energies fall between approximately 57 and 69 keV. These appear as the characteristic spikes on the emission spectrum. Characteristic radiation makes up roughly 10 to 20% of the beam above 70 kVp. For mammography units that use molybdenum or rhodium targets, the characteristic energies are much lower, around 17 to 20 keV, which is exactly the energy range needed for soft tissue breast imaging. The summary table on this slide organizes the beam properties you need for both the registry and clinical practice. Beam quality is penetrating power, controlled primarily by kVp, secondarily by filtration. Higher kVp equals harder beam equals greater penetrating power. Beam quantity is the number of photons produced, controlled by MAS. Double the MAS and you double the quantity and double the patient dose. Simple, linear, direct. Beam intensity is energy per unit area, affected by kVp, MAS, filtration, and SID, and it decreases by the inverse square law with increasing distance. The HVL, half-value layer, measures beam quality as the thickness of aluminum that reduces beam intensity by 50%. Higher HVL means a harder, better filtered, higher quality beam. The 15% rule, increase kVp by 15% and cut MAS in half for equivalent density. Approximately 50% dose reduction. MAS reciprocity, any Ma and time combination that produces the same MAS gives equivalent exposure. 50 mA at 0.1 seconds equals 5 mA at 1 second, both deliver 5 MAS. 3 X-ray production questions in the ARRT style. Think before the answer appears. The answer is C, Bremsstrahlung radiation. Bremsstrahlung results when electrons decelerate near the tungsten nucleus, releasing lost kinetic energy as X-ray photons across a continuous spectrum. It makes Up 80 to 90% of the diagnostic beam. Characteristic. Radiation makes up the remaining 10 to 20% above. Approximately 70 kVp. The answer is B. Area decreases, mean photon energy increases. Increasing kVp shifts the entire spectrum to higher energies, raising mean photon energy. Having MAS reduces the quantity of photons produced, decreasing the area under the curve. This is the 15% rule in action, equivalent image density, with approximately half the patient dose. The answer is B. The applied kVp must exceed the K-shell binding energy of tungsten. Approximately 69.5 keV. Characteristic radiation. Requires the incoming electron to eject an inner K-shell. Electron from tungsten. The K-shell binding energy for tungsten is approximately 69.5 keV, so characteristic. Radiation only occurs when kVp exceeds approximately 70 kVp. You covered thermionic emission. An electron acceleration, the emission spectrum at multiple kVp values with chart analysis, Bremsstrahlung radiation and its mechanism, characteristic. Radiation and its threshold, and the beam quality and quantity. Summary table. The physics of the beam is the foundation of every technique decision you make.